So today we're going to focus all on E2 reaction mechanisms. E2 reactions make up a big bulk of Chapter 8 in the textbook. And let's do a little bit of review of the E2 reaction mechanism. What's the reaction rate equation? Yeah, so it's starting material times the concentration of the base. So it's a second order reaction that's concerted. So we'll write that down. It's a concerted second order reaction. I've got this recording, right? Yep. And we said that the rate is equal to this rate constant, little k, times the concentration of our substrate. That's the thing with our leaving group on it, times the concentration of our base. And yesterday we talked a lot about choosing the appropriate base for our reaction. Oftentimes we need to use a non-nucleophilic base, or else it will do some SN2 chemistry. So things like DBU, DBN, sodium hydride, potassium terbutoxide, those are all really common non-nucleophilic bases. The other big thing we're going to be talking about today is which proton gets removed during an E2 elimination reaction. And what do we remember from yesterday? Beta. Has to be a beta proton. So the big thing is beta proton is deprotonated. And the new thing we're introducing today is that this beta proton must be anticoplanar. You guys remember talking about anticoplanar and syn coplanar in the Newman projection section? It's coming back. So let's go ahead and take a look into what I mean by this. And for this example, I'll show you guys how to use Newman projections. Whoop, no D in there. And so we'll do a little review. So in this first example, we're going to have a generic R group. Oop. And I'm going to have a methyl group coming off here with 3 hydrogens. And I'm going to label these hydrogens with different colors. So we've got a red one, we've got a green one, and we've got a blue one. And then up here, we've got our leaving group. And we've got a second hydrogen, right? So in this case, we need to identify the proton that is anti-coplanar to our leaving group, right? So the question is, will it be our blue one, our green one, or our red one? So let's quickly draw a Newman projection. And I want you guys to imagine looking down this bond. Let me clean this up. So remember, with Newman projections, we've got that 3-line intersect in the front, and then in the back, we've got some groups coming off as well. What would be coming off the very straight up and down bond? Blue. All right, what about this position over here? Green. All right, so we've got a green proton. That leaves our red proton left over. All right, in the back, what's sticking straight down? R. What's going to the right? H, and that leaves our leaving group over here. So if we were to look at this, we could say immediately, hey, this green proton is anti-coplanar to this leaving group, right? Whoop. The reality is this sigma bond can rotate, but at least if we're looking at it in this conformation, that would be the anticoplanar beta proton, right? So now let's go ahead and do our E2 reaction. So, whoop, I'm going to redraw our starting material. Whoop. Got a hydrogen, and we've got our leaving group. We've got our red proton here, our green proton, and our blue proton. And if we've got some generic base, let's even just assume that it's sodium hydride. This sodium hydride would like to deprotonate this green one because it's in the correct orientation where it's anticoplanar. It will clamp down and then kick off this leaving group, all in one concerted step. All right, so now the question is, which proton will be on which side? So let's consider our two examples. Oop. And I'm just going to draw out the skeletal formula, and then we have to figure out which protons are where. So we know the carbon with that R group had that black proton on it. The question is, will this blue proton be on the same side as that hydrogen or on opposite sides? I'll give you guys a minute to discuss with your neighbor, but let's try to come up with some sort of explanation as to which one of these will be the likely reaction product. Mm-hmm.
Like if it was coplanar, what would it be? On top right.
So syn-coplanar would be if it were in the eclipse conformation and one of those hydrogens were overlapping with the leaving group. So anticoplanar, if you remember, just means that this position is on the opposite side as that position.
I actually forgot.
Oh, that's okay. It's a good thing to review. The answer is not resonance. Dang it. How many of you guys think you maybe have a decent guess? A couple people? You guys want to see my super handy trick? It's why I love doing the Newman projections. Is it can be really tough to tell, but you see how I've circled the two anticoplanar positions? Now what I do is I circle these positions over here, and these will be cis to one another in the product. Do you guys see that? How they're on the same side in the Newman projection? That means they'll be on the same side in your resulting alkene. So knowing that, which one's going to be our most likely product? The left one, right? Because the blue proton should be cis to that black proton. That means that this one will be our likely product. We won't observe any of the one on the right. However, with sigma bond rotation, we could. I'm just trying to get you guys to think about which one will show up on which side. So that would be our correct product. And then we also have our conjugate acid, which in this case is going to be H2 gas. And we've kicked off our leaving group. You guys want to try a harder one? All right, let's try a harder one. All right, in this one, I'm going to give you a full molecule. And I want you to help me determine what the product would be, including stereochemistry.
Is that an O or a D?
That's a D for deuterium. So let me emphasize that. The D equals deuterium. And in this case, we're going to react this with sodium hydride or a generic strong base. So I'll give you guys a minute to work on this, but try to do the same thing with our Newman projection that we did previously. I'm just going to erase this right now so we have room to draw our Newman projection. And remember, with Newman projections, it's always a good idea to look down that alpha-beta bond. That way you can identify if that beta proton is truly anticoplanar to your leaving group. So just like we did before, I'll draw in my pretend eyeball, and we'll look down that bond.
Trying to find the product, so the E2.
Yeah, let's try to do the Newman projection and then see if you can work through the product. I'll get us started with this Newman projection though. And I want to point out a problem. Oh, let me make this bigger. There we go. All right, what's the problem with our Newman projection right now?
The hydrogen's not in the anticoplanar.
Yeah, if we look at this right now, our bromine and our ethyl group are anticoplanar. How can we fix this?
Sigma bond.
Yeah, sigma bond rotation. So let's do a rotation so that we do end up with a hydrogen that's anticoplanar. So we're going to move this hydrogen over, this ethyl group over, and this methyl group over. Oh. Okay, now our hydrogen's anticoplanar, our methyl group's in the top position, and we've got our ethyl group down here. Looks pretty good to me. So now we've got a bromine, that's our leaving group, that's anticoplanar to our beta proton. And then, just like we did in the previous example, I like to circle the groups that are remaining. So these will be cis to one another, and these will be cis. And I'm using cis in a loose sense, just meaning that they're on the same side of the double bond. Okay, so now let's go ahead. And what I want to do is redraw this using a 2D conformation, and I'm going to redraw this down here. So let's redraw this back into our bond line structure, similar to what we had before. So we've got our bromine and our hydrogen. That back carbon we know stayed put. However, now we've got a methyl group sticking up, right? Our hydrogen is a dash, and then this ethyl group is now a wedge. It's the exact same structure, just with that sigma bond rotated a little bit. Okay, now we can do our E2 reaction. We know that it's going to go after this proton. Whoa. And let's draw our product out. And then when you're done, determine whether or not that product is E or Z. So this is our product. Is it going to be E or Z? Ah, tricky. So remember what we do with E or Z is we have to assign priorities. So if we look at this carbon in red, what's going to be higher priority? The ethyl group, so we'd say, all right, that's priority 1. If we look over here at the carbon in blue, what's going to be higher priority? Deuterium or hydrogen? Deuterium. So this would be priority 1. So would this be E or Z? Z, same side. So we've formed our Z alkene. The interesting thing with this reaction is a lot of students will say, well, is it possible for us to get any of the E alkene? What do you guys think?
Yes. I mean, I think
Not,
rotating before that.
not if there's only one beta hydrogen.
Ah, that's a good point. So you said there's only one beta hydrogen, right? Which means if we rotate it, we're kind of stuck. This Newman projection that we've got drawn up here is the only possible Newman projection where we have a beta proton that's anticoplanar. That means we're stuck and we can only get one product out of it. We're not going to observe any of the E isomer. So we'll say E isomer is not observed, simply due to the reliance on that proton being anticoplanar.
Does it have to be anticoplanar because of sterics? Because of the leaving group? Is the electron log is leaving? Or why exactly would we make it anticoplanar?
It gets more into how the orbitals are aligned, but in order for this reaction to occur, you have to have the same orbitals aligned along all 3 of the groups, that beta proton, the new pi bond that you're forming, and the leaving group. If you've got it in any other position but anticoplanar, you don't have alignment of all of those orbitals anymore. So think of it like dominoes, right? Your dominoes have to be lined up in order to kick something down. Yeah. All right, so now I've got to introduce some terminology and some vocab. The first vocab term I want to introduce is something called stereospecific. Stereospecific is a term used for a reaction that only gives one stereoisomer as a product. If we were to look at this above reaction, you see how it only gave us one stereoisomer? This would be referred to as a stereospecific reaction. There's another term that's often used that can be very confusing, and that's stereoselective. A stereoselective reaction is a reaction that gives a mixture of stereoisomers but one is major and the other is minor. So the way I remember this is when you want something that's specific, you only want one thing. When you're selective, you might say, you know what, I want a hamburger. It doesn't matter if it comes from McDonald's or Burger King or Jack in the Box, but I selectively want a hamburger, right? Specific means I have to have my Big Mac. So it can be super confusing because the terminology is very similar. Stereospecific reactions, however, only give you one product. Think of specific demands that you might want. Selective just means you'd be willing to accept a handful of different things. So stereoselective reactions and stereospecific reactions will show up occasionally in this chapter. The last one that I wanted to introduce is something called regioselective. And a regioselective reaction is a reaction that gives an unequal mix of constitutional isomers So there are additional terms that you might see in the book as well, like enantioselective or enantiospecific. That's referring to a reaction that primarily produces one enantiomer over the other. However, stereoselective reactions could be either enantiomers or diastereomers that you're comparing. So there are a few more, but these are the main three that I want you guys to be concerned with. All right, let's do another one. Go back to our practice problems. All right, for this one, let's consider an analogous reaction, where again we've got deuterium, that's our D. Got my hydrogen in black. And for this one, I've got two different protons coming off. I've got a green one, and I've got a blue one.
Is that deuterium?
Yeah, this is deuterium. Sorry, this should be a hydrogen. The black one's deuterium. That was my fault. All right, let's imagine doing an E2 reaction with this compound. But this time I'll give you guys a hint. There's more than one potential product. So let's go ahead and try to do Newman projections and see why there could be more than one potential product. How many of you guys think you got the first Newman projection? All right, that's good. We're getting Newman projections. All right, up top we've got our methyl group. On the right we've got our hydrogen in blue, and on the left we've got our hydrogen in green. Down below we've got our deuterium. On the right we've got our hydrogen, and over here we've got our bromine, right? So if we look at this, we've got an anticoplanar beta proton. We've got the blue proton in this conformation that's anticoplanar to that bromine. Are there any other possible anticoplanar beta protons? Yeah, we could absolutely rotate this. So let's rotate that front carbon, just like we did in the previous problem. And this time I'm going to rotate it kind of going this direction so that this green proton is now located where that blue one is, so we're rotating it counterclockwise. Okay, that means our blue proton's up top, and our methyl group is over here. And there we go. So now in this conformation, we've got a couple different products that might be possible, right? So let's go ahead and consider this. And I want to redraw each of these using our Newman projector, or our 2D bond line structure. So in our first one, we said we could deprotonate that blue proton. So I'll just go ahead and write our generic base. Clamp down and kick off this bromine. So what would our product look like after this? And then what I want to do is, this was our Newman projection number 1. So I'll write Newman number 1 above it. And then we want to do a second reaction for Newman number 2. And for this one, we're grabbing the green proton, clamping down, and kicking off our bromine. How many of you guys feel pretty comfortable predicting the products out of this? Pretty good? All right. So for product number 1, I'm just going to erase these green circles just so we can clearly identify our cis groups. For Newman number 1, we said this methyl and the hydrogen will be cis, and this hydrogen and the deuterium will be cis. And we need to make sure that we keep track of which carbon everything's coming off of. So for this one, we'll get a methyl group that is cis to a hydrogen. Whoop. And then over here, we've got the hydrogen in green. And we've got this deuterium in black. Down here, it looks pretty similar. However, let's go up and just double check. Now we've got 2 hydrogens that are cis, and now that methyl and deuterium that are cis to one another. Deuterium and methyl. Right? So these are our 2 different products that we could get out. Are we going to get one or the other?
Both.
Yeah, we'll probably get both, right? So in this case, this E2 reaction will produce a mixture of stereoisomers. Does that mean it's going to be stereospecific? No, stereospecific reactions only produce one product. In this case, do you think it'll even be stereoselective? Are we going to get one of these in a higher concentration than the other, or do you think it's going to be roughly the same? Yeah, roughly the same. So in this case, we know that it's not going to be stereospecific or stereoselective. We would probably get close to a 50-50 mixture out of this. So it's kind of an odd example. All right, what's the relationship between these 2 compounds?
Z or E.
Well, are they constitutional isomers, diastereomers, and enantiomers? Are they giraffes and rabbits? Diastereomers, right? So if we look at these, they've got the same connectivity, but they are not mirror images of one another. So these would be a 50-50 mix of diastereomers. All right. Now I'm going to give you guys more of a challenge problem. And I want you guys to work as a team to solve this. All right, for this challenge problem, it says R2-bromobutane is treated with a strong base. A strong non-nucleophilic base. What products will you get? And I'll give you guys a hint. There are 3 products. So I'll give you guys a minute to work on this, but try to work through it and then check with the neighbor to compare your answers and see if you guys are both coming up with the same sort of explanation. Are you guys all able to draw our 2-bromobutane?
Yes.
I hope so. I'll get you guys started though in case you're having trouble. We draw our backbone, butane. Should the bromine coming off of this carbon right here be a dash or wedge? A wedge, right? So if we look at this bromine should be a wedge. If you're having trouble with stereochemistry still, please come talk to me or go to the WTC so we can get this taken care of, because you need to know it for chapter 7 and 8. If you guys think you got it too, you can give me a thumbs up so I can kind of get a gauge on how many people
Got what?
got the 3 different products out of this reaction.
It's 3 different. You tack it different. Whoa. Different. You tack this one. You tack this one. That's what I'm saying. There's 2 here, so you can take this one, or you can take this one. I think that'll give you 2 products. These will be the same 2 products. Obviously, this one too. Projections, right?
But again, there's 3. I was thinking,
I mean, this
I was thinking
Newman.
I know.
those 2, and then there's another beta carbon.
All right, for those of you that are struggling, what I like to do in these problems is draw out my beta protons, right? So let's take a look at that methyl group on the left. We've got 3 protons. Are they equivalent or non-equivalent? Does it matter which one we take? Doesn't matter because they can spin around in space. They can all take that anticoplanar position, right? All right, and then our other beta protons are coming off here and here. We've got 2 different types. Are they the same or are they different?
But
I would say they're a little bit different. So let's do this. Let's color code them. And I'll say this one's blue and this one's red. All right, let's do reaction number 1. reaction number one, I'm going to do the easy one. We'll just go after one of the black protons, and we'll say, all right, one product could be we kick off this proton, and we make this product, right? Easy enough. What would this product be called? We number it. We've got 1, 2, 3, 4. So it's a butene. Specifically, it would be 1-butene. Can we label it as cis or trans or E or Z? No, it's only got one substituent. So it's just 1-butene. That would be one product. Let's try this again, though. And this time, we know that that red proton's anticoplanar. So I'll draw in this red proton over here and this blue proton over here. All right, so now we're forming our double bond between carbon 2 and 3. Will this be cis or will it be trans? You guys think it'll be trans? Okay. So if we do this, this will be trans, and you can check that with the Newman projection. So in this case, we would have trans 2-butene. That could be one potential product. Or we could do a rotation, right? And we could push that blue proton into the anticoplanar beta position. And we could say, all right, what if we push this blue proton over here? That would mean our methyl group would have to slide down over here, and our red proton would be sticking up. Let me clean this up a little. And now if we treat it with the strong base, will we get the same product or a different product? Yeah, you get your cis product out. So we get cis 2-butene. The thing I can't emphasize enough with chapter 8 is try to consider all of your beta protons. And you may need to do some Newman projection rotations to identify which ones can be anticoplanar, and that may impact your chemical outcome. But oftentimes you get more than one product out of an E2 reaction. And we're going to talk about that a lot more tomorrow. But what I want to do now is switch gears to the problem of the day I told you guys we'd do in class. So if you have your problem of the day, pull it out and we'll work on it. But what I want you guys to do is consider reaction A versus reaction B, and then consider which one's going to occur at a faster rate. But remember, that beta proton must be anticoplanar to the leaving group. So you may need to consider your chair conformations when you're looking at this.
That's what he said.
I'll give you a hint too. Consider chair flips.
Are we turning this in?
Nope, this is just for your own joy.
So joyful right now. Forgot how to draw a chair.
It wasn't that long ago.
I could barely draw it when we were doing that. My chairs don't look like chairs.
So my first word of advice is draw both chair conformations of your starting material. And then after you've drawn both chair conformations, circle the one that's more stable. Just like we did on our exam 1. Let me clean up my chairs a little bit. I don't like these.
Everybody else is just trying to draw a chair. Okay, so
I'm so glad I don't have to-
this chair must be executed. Based on
One,
I draw really skinny and really fast, and I'm really skinny.
6, 4, 5, 6. So I'm going to number my carbons too, just for simplicity's sake.
Some of those days we didn't just show things like that.
Four, 5. You guys want to help me build some chairs? Let's start with reaction A. So I've got carbon 1 labeled right here. Sorry, my numbers can be a little hard to read. But should that bromine be axial or equatorial if we're looking straight up and down on the ring? Axial, right? It's sticking straight up towards our eye, so I'll just put in a bromine right here. All right, that means on carbon 1 on the other chair flip, it should be axial or equatorial. Equatorial, not too bad. All right, on carbon 3, should that methyl group be axial or equatorial? Axial. So I'll write CH3. And then what about carbon 5? Should that methyl group be axial or equatorial? Axial. So we'll go ahead and we'll say, all right, we've got all three of those. So it looks like all three substituents in that one chair are axial. And then in the other chair, that means that they must all be equatorial, right? Which one's more stable, the left one or the right one? The right one. All right. So we'll say more stable. The only difference between reaction A and B is that bromine coming off is switched. So let's just quickly plug in those same substituents. Oop. However, now this bromine's equatorial instead of axial. So if we do our chair flip, right, this carbon 5 becomes equatorial. Carbon 3 is now equatorial too. However, in the 1 position, this bromine is now axial and it's underneath. All right, this can be a little bit tricky, but which one's more stable? The left one or the right one? Assume that bromine's smaller than a methyl group too, for the most part. 2 methyl groups will win out over the bromine. That'd be the right one too, right? We want to minimize those 1,3 diaxial interactions. The one on the right has minimized 1,3 diaxial interactions. All right, so now let's take a look at these chairs in real life. I need to only hold one at a time. All right, so can you guys see? Oh man, I've got these flipped. Oh man, what am I doing? Hang on, guys. I built it too quickly before coming to class. All right, so this would be the one where they're all axial, right? You guys see that red position's bromine? Does it have an anticoplanar beta proton? Let me pull these groups off. What do you guys think? Anticoplanar beta proton? Yeah, I'd say if you look down that alpha beta bond, there would be an anticoplanar beta proton.
It would be
So
the
I'll-
axial ones on the left.
Yeah, exactly. So it must be another axial position that's going to be your anticoplanar beta proton. So if you look down these bonds, you can see an anticoplanar beta proton, right? However, your leaving group must be axial, and the beta proton must be axial too. Let's do a chair flip and see what happens. In the chair flip, can you guys see the bromine now? Does it have any anticoplanar beta protons? No. This is a really important thing to remember for E2 chemistry. Is for an E2 to occur in cyclohexanes, your leaving group must be axial, and your beta proton must be axial. All right, so if we look at these, we can say, all right, which of these can do E2 elimination? Well, we can say immediately this one can't because that bromine's not axial anymore, right? And then this one can't because that bromine's not axial. Does that make sense? Your leaving group's got to be in an axial position for an E2 to occur. Sometimes building the model kit can help as opposed to seeing it on a 2D paper. So knowing that, which reaction do you think is going to occur faster, reaction A or B? B, right? B's got the more stable chair conformation with that leaving group in the axial conformation. That's a big driving force for making reaction B a slightly faster reaction over reaction A. In order to get reaction A to go, you actually have to force that chair into the less stable chair conformation, and then it can do E2, but it really prefers to be in that more stable conformation in equilibrium. So the problem of the day that I gave you guys today is a continuation on cyclohexane stuff. So really try to pull out a model kit and build this and see if you can identify your anticoplanar beta proton or protons. And remember, your leaving group must be axial, and your beta proton must be axial as well.
So do we all get like whole points on that POD?
We don't get any, because I saw it in there as nothing.
I just dropped it from the assignment list.
I was hoping to like extra.
So because reaction A's reaction was able to do it, it made a product.
So in this case, I was just asking about reaction rates. Which one will occur more quickly? Reaction A, in order for it to do an E2, it must go through an unstable chair conformation or a less stable chair
Why
conformation.
is that one unstable? Because that has the axial.
Exactly. You've got these 1,3 diaxial interactions in here. And these 1,3 diaxial interactions destabilize that chair.
So even though it was,
Another way of thinking about this, right?
so if we had done the chair flip, that would have been more stable. Which
Let's say you've got 80% of this chair in equilibrium and 20% in this chair conformation, right? On this one, same sort of thing. You've got 80% versus 20%. Just think about it in terms of the rate equation, right? If you're dropping the concentration of your reactive starting material down to 20%, that's going to be a lot lower than if your starting material concentration were higher at 80%. Because these are your reactive starting materials from this equation.
When I'm reading, I'm like,
I was thinking